We did observe a system which is under the influence of two forces. One was the spring force and one was the viscosity. The second order differential equation can be written in this form. And then we did modify this and we have written it in this form. Now, our next case that we are going to take up is case number 3, where we're basically considering beta square is equal to omega naught square. Observe that there is no oscillation and there is something which we call as critical damping. But for this, we are not going to start with this final solution, although we can do it. And if we do, what we observe is that if beta square is equal to omega naught square, this part becomes 0 and this part also becomes 0. So e to the 0 will become 1, this will become 1, and it will have only two terms, c1 plus c2 into e to the power minus beta t. That means it doesn't have any cos or sine term, and in simple words we can say that there won't be any oscillation, because we have seen that if it's an oscillatory motion function. But what will be the form of c1 and c2? And for that, what we are going to do is we are going to start with this expression, which is expression 1. So let's begin this derivation, and let's take a new page, and I'll start with study of case 3. So if we look in case 3, we have got beta square is equal to omega naught. Say that b square is equal to 4am. So I'm going to rewrite expression 1, and we have written that expression in the form of beta, or in terms of beta, so I can write it down as d2x dt square plus 2 beta dx divided by dt plus omega naught square. I've discussed about this derivation in detail in the previous lecture, so if you're confused, you can just refer to that. Now we have this relation from expression 1. Now we want to solve it. So, we used a trial solution and we actually solved this expression and we found out the value of alpha previously. But now we're going to see how we're actually getting the solution for this. Okay, so that's also a very important part of our learning. So what we're going to do here is, let me just remodify this, and maybe I can write it like this, plus 2 beta d dt plus omega naught square. I can have this term, and whatever is left, I'll take it out. So it's x. So I'll take x out of this bracket. And this is basically acting as an operator. And we can, in fact, write it down in such a way. Okay. So let me just, help you out in writing it down in a different way altogether. In this particular case, we see that omega naught square is nothing but beta square. So what we can do is we can replace this omega naught square with beta square. So let me not write down an additional line. You also don't need to do that. I think it's very obvious. You can just simply write it down. So you see, you can actually write it down in a different form altogether. And let me just write down that form, and then I think it will be more clear to you. I can write it down as d dt plus beta into d dt plus beta. So I can separate it out, and I have to separate operators now. And the good part here is I don't have a second order differential equation. I've broken it up in such a way that ultimately I'm going to get a first order differential equation. But then, if you multiply these two terms, you are definitely going to get back this. Okay, you can check it. ddt of ddt is d square dt square. You get the first term. Beta into ddt, you get one term here, and then you get ddt of beta, the other term. So it will be twice of beta ddt, you get the third term, and you can multiply beta, and you're getting beta square. So that means I've written the same thing, right? What I am going to do now is we are going to do a replacement here, and let me just show you that replacement. So what we're going to say is let one of the term d dt plus beta into x, let it be y, right? And if you do that, this term actually gets modified. So what we can do now is we can write it down as d dt plus beta, right? That's the first term, d dt plus beta, and this entire term I'm considering as y. So I can just simply write it down as y is equal to 0. So we have done a substitution here, or what we can do is we can simply write it down as dy divided by dt plus beta into y is equal to 0. So we have this expression. Now solving this expression is kind of easy. I don't think it's you know very difficult. You can understand this very easily. Let's solve this expression. Okay. So if we solve this, what we can do here is we can take the terms. So I can just simply write it down as dy divided by dt is equal to minus beta y, and then I can do a bit of cross multiplication. I can simply write it down as dy divided by y is equal to minus beta dt. I want to solve it for y, so what I can do is I can integrate this. So let's integrate this on both sides. If we do that, this is nothing but log of y. Please remember this is a natural log, right? And this would be minus beta. We can take it out as a constant. Integrate dt is nothing but t. And then, of course, we will basically have a constant. So let's say this constant is c. Let's use the property of logarithm, right? You have log of y, you can just have y. And on the other side, everything will be to the power e, e to the power the all the terms. So it will be minus beta t plus c. Here we can again, separate it out. And what we can do now is we can simply write it down as e to the power minus beta t into e to the power c. C is a constant, e would be 2.71, so that's again a constant. So I can take this entire term to be another constant. I can simply write it down as d e to the power minus beta t. So this is our y, and what we can do now is, okay, we are going to solve it further. So what we have now is y is equal to, let me just rewrite this, y is equal to d e to the power minus beta t. But y is a term that we have introduced, it was not there. Y is nothing but this particular term, so we are going to more or less replace it here. So what was our y here? So if we just check, this was our y, so we can just replace it here, and let's see what happens. So if we replace our y, so it would be nothing but dx divided by dt plus beta x is equal to d, capital D, e to the power minus beta t. Now we are basically having this, okay, and we need to solve it further to actually get our solution for this, for x run, okay. So what we can do now is, let me just note it down for you, okay. We can divide throughout by e to the power minus beta t. So if I divide here, it will be d dt of x into 1 divided by e to the power minus beta t. If you take it in the denominator, you can just simply write it down as e to the power beta t, and then plus beta x is there, and then again I divide it on this side as well, so I can write it down as e to the power beta t is equal to d e to the power of minus beta t divided by e to the power beta t. So that gets cancelled, so I'm left out only with the term d on this side. Again, there is something which is a bit tricky, but I think it's easy to grasp. It's d dt of x e to the power beta t. If I write down this term and I expand it using the product rule of differentiation, you are basically going to get this. See, this is a function differentiation with respect to time. X and this exponential term both are dependent on time. So you have to differentiate both, right? So if you use this formula, what you can do is this d dt of a b, and both a and b are functions of time. So it will be a d dt of b plus b d dt of a. If we do that, we are going to get back this relation. So you can use this formula and check if you're getting the same result. And that's going to be that, right? So now we have this term, and what we can do now is we can take the d of x e to the power beta t is equal to capital D, which is a constant, and just multiply it with dt. Now, if we integrate this, okay, we can integrate this term, and we will see that this would be nothing but this would be, if we just integrate this is going to be very simple. You are going to get x e to the power beta t is equal to d integration of dt is t plus a constant, let's say e. Okay, so we are going to have this form, and what else we can do is we can take x on one side, which is actually a function of time t, and this can be written as dt plus e, and you take this e on the other side or divide both by e to the power beta t, you're going to get e to the power minus beta t. So this is the solution we have when beta square is equal to omega naught square. Okay, so this is important, and this will be, you know, a relation which doesn't have any cos function or sine function, but only has an exponential function. That means there is only going to be a decay. So if we basically just try to plot a graph, okay, and we plot a graph between time along the x-axis and the displacement along the y-axis for this particular term or this function, we are going to get something like this. This will be an exponential decay here, right? So this is the solution, right? And this is eventually going to tend to zero, because if you observe here, if t tends to zero or infinity for a very large part of time, after a very infinite amount of time, x will obviously tend to zero. So that means this is going to touch zero at a very high value of time. That's obvious, right? Because it's e to the power minus beta t, so e to the power minus infinity, you divide it by this, you're going to get a term which would be very large in the denominator. It's going to be zero eventually. Now, that means that we can simply conclude here that there is not going to be any kind of oscillation here. There is no oscillation as such, because there are no sine term and cos term, but of course there is a decay. Okay, so it moves towards decay, or maybe rest, we can say. Okay, but exponential decay, there is an exponential decay, or we can say that the system will move towards rest, move towards rest. One more thing that you need to know is that, it's basically called critical damping, as we have seen. The term is critical damping. And why it is called critical? Because it's somewhere between the over and the under damping part. Okay, it lies between over damping and under damping. So this basically separates the over damping and the under damping part. Over and under damping. So in the last lecture we did see under damping. Today we are seeing critical damping, And then finally, we are going to check the overdamping part. So overdamping, as we have seen, the condition for overdamping will be this: beta square is greater than omega naught square. So next we are going to check for overdamping, and that would be case 4. So you have to, don't need to remember all the relations. You have to remember just the final result and use the conditions accordingly to check for underdamping when beta is equal to 0, critical damping, and overdamping.